The most notable of these were some experiments that led to what's called the photoelectric effect. Now, what was happening was that light was being shown onto a piece of metal, and the metal was giving off electrons. But what stumped researchers was the fact that the metals could only give off electrons if the light that was being shown on it was at certain frequencies. So this was an issue. It couldn't be explained because at the time, they just believed that light was a continuous wave of energies, not specific values of energy. So to help explain what was going on, a guy by the name of Max Planck came along, and he came up with the idea, or tried to explain the photoelectric effect. But in order to do so, he had to revise how everybody believed light behaved as. So they had to revise their view of light. And he figured out that metal, a piece of metal, like the one shown here, could only release certain little packets of energy, and he called those quanta, or quantum is the singular version. Certain frequencies of light would have certain energies that would be strong enough to eject one of these quanta out of the metal. So what does this all mean? Well, to sum it up, according to Planck, light is not a continuous wave. It's not continuous like a wave, but rather it exists in particles. Now, this was a radical idea at the time, and of course you can imagine that there was lots of resistance to this. But Planck, in order to help explain this photoelectric effect, Planck came up with a new formula, and that the energy of these quanta can be found by taking a constant that Planck came up with, h, times the frequency of the energy. And this is something you need to know down here. This is called Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. Notice that that's a multiplication symbol. Please don't get this confused with Avogadro's number, even though it looks fairly similar. So this was Planck's idea, that there's a relationship between the energy and the frequency of radiation. But again, he's still viewing light as existing as these particles. So to help remedy everything, Einstein, maybe you've heard of him before, Einstein came along and came up with an even better idea at the time. He kind of merged the two ideas and said, you know what? Light is both a wave and a particle at the same time. It's called the dual nature of light. So light contains photons, or these little particles of energy, and these photons travel in waves. So it's both a wave and a particle at the same time. And each of these photons has a certain energy. And it can be calculated by that same equation that Planck came up. You'll notice the only difference is the addition of this, that the energy of a photon is found by taking Planck's constant times the frequency of the radiation. So now it shows that there's a direct relationship between energy and frequency of a wave. So let's do one of these problems. So a typical problem might be like this, that you find the energy of a photon that has a frequency of 3.55 times 10 to the 17th hertz. We have our equation written down, and if you need to pause the video so you can do this problem, that's a great idea, but this problem should be in your notes. Energy is H times V. So energy is going to be Planck's constant, 6.626 times 10 to the negative 34th joule times second, multiplied by the frequency, 3.55 times 10 to the 17th. And instead of writing hertz, I remember that hertz is the same thing as inverse second. Now I do that so I can see what happens to my units. Seconds times inverse seconds results in those two units canceling out. And look what I'm left with. I'm left with an energy unit. So then I pick up my calculator and I type it in. And you'll notice you're taking something times 10 to the negative 34th times something times 10 to the 17th. So you will get an answer that has a negative exponent. And when you type it in, you'll get 2.35 times 10 to the negative 16th joule. And that's the energy of a photon. That's a singular photon if we know the frequency of that photon or that radiation. Are you guys having fun yet? This is kind of a wacky chapter. It's very theoretical, but we're almost done. So here we go. So far we've discussed light and its nature, and now we know that light is both a wave and a particle, but we haven't talked about the atom in a while. Kind of disregarded it for the last 10 minutes. So the question is where are the electrons? Are they really just anywhere outside of the nucleus as Rutherford claimed? Well, the person who contributes to this idea is a guy by the name of Niels Bohr, B-O-H-R, and he was studying how certain gases glowed or gave off light when they were exposed to electricity. Think of a neon sign, or you can look at this picture here. This is hydrogen, and when hydrogen is exposed to electricity, it gives off a pink glow. And different elements glow different colors. And Bohr found that if you pass that light that came off of that spectrum tube, if you pass that light through a prism, then the light gets separated into distinct lines, as you can see over here. And these are called the line emission spectra. You can see how the prism breaks them up into different colored lines, and then they're showed, the hydrogen ones are shown up here. So every time hydrogen was exposed to electricity, it would give off a certain pattern of lines, of colored lines. And these patterns of lines are always the same for the same elements. As you can see below, here's the line emission spectra for mercury, for strontium. So the question is why? Why do these elements give off these patterns of lines? Well, Bohr figured out or hypothesized that electrons exist in a low energy or a normal energy level that he termed the ground state. And when electricity passes through the gas, the electrons absorb energy and become excited, causing them to rise up to a higher energy level called the excited state. But just like if you throw a baseball up into the air, it can't stay in that higher state for long. And so these electrons can't stay at that higher energy level either. And so they fall back down to the ground state. And when these electrons fall back down to the ground state, they emit energy in the form of light. And that's detected by the line emission spectra. Another way to think about that is just like if you throw a baseball into the air with a certain amount of energy, it's going to come back down with a certain amount of energy. And if we go back to the idea of light, if we know what color the light is, so for hydrogen gas, Bohr could tell what the different colors are. We can relate that to frequency because we know that there's a relationship between wavelength and frequency. And if we can get the frequency from the wavelength, then we can plug that into Planck's constant and figure out how much energy those electrons were giving off as they dropped back down. Because that light that's being given off is being given off as a photon, as a particle of light. So now we've got a relationship between all of these equations, between the original wave equation that relates to the speed of light, and now to Planck's equation. Let's look at it in a different way. If we think of this bottom line as the ground state and the top line as the excited state, electrons can move up in energy. They can absorb energy if they are exposed to light. They stay up in this excited state just for a few seconds, and then they drop back down. And when they drop back down, they give off extra energy in the form of light. That's the photon, and we can measure that energy because of that equation. And so what's the big deal? That's the question here. Well, because we can measure that energy and that the lines in the line emission spectra were always at certain colors or frequencies, then that means that the electrons were only existing in specific energy levels. So we have to revise how we viewed the atom. So according to Bohr, electrons exist at certain measurable energy levels. And we call those orbits or energy levels, a lot like the planets surrounding the sun or orbiting around the sun. If this were the sun, then this would be the orbit for Mercury, Venus, Earth, etc. Now, unlike Rutherford, who believed that electrons were just somewhere outside of the nucleus, Bohr believed that the electrons exist at these specific energy levels. Now, if an electron exists at a certain energy level, let's say it normally exists here, it can never exist here in the middle, but it could absorb enough energy where it could get bumped up to the next energy level. And if it did get bumped up to the next energy level, it would fall back down and give off energy in the form of light, because it's giving off energy in the form of photons. The same electron could absorb even more energy and move up 2 orbits. And when it falls back down, it gives off a different frequency of light. So it shows a different color. And that's where the different line emission spectra came from. They're explained by electrons existing in specific energy levels. And this is where we're going to leave off for our current topic discussion. And the next topic discussion is specifically within those energy levels, what are the electrons doing? Because it gets even more complicated than today's discussion. Please come to class with your example problem solved and any questions that you may have about this topic.